Hey, hello everybody. Today we're going to look a little bit deeper into waves, but not super deep. You're going to get some practice though today at applying this particular formula. Now this is the only formula that is on your formula sheet for waves, and pretty much the only one we're going to use this unit. Um, and so this is a new letter for us. This is a Greek letter lambda, which you've probably heard before. Um, but lambda stands for wavelength. Okay, so if you look down here at this drawing, here actually, wavelength is the length of a complete cycle. So wavelength on this drawing would be from here to here, for example, from this crest to this crest. Or you could measure it from this trough to this trough. That would be a wavelength as well. You could also measure it from this point right here to this point right here. That would also be a wavelength. Or from this, let me put a triangle on that. This point to this point. Okay, just as long as you have a complete wave cycle captured, that would be your wavelength. And it would be measured in meters. So it's just a normal length measurement. Now you calculate that by dividing the wave speed. V is again going to represent speed, and it's still going to be in meters per second. And you divide that by the frequency of the wave. Now the frequency is measured in hertz, and hertz is translates to waves per second. So, for example, your maybe your favorite radio station is DVE, 102.5 megahertz. So that would be 102.5 million meters waves every second. Okay. The one thing that you're going to have to use today is this whole idea of period and frequency being inverses. So if they tell you something about how long the wave takes, or how long it takes for one complete wave cycle to pass, they're telling you the amount of seconds. They're telling you the period of the wave. You find the inverse of that, and that will be the frequency of the wave. Okay, so just keep that in mind. Also, just keep the units in mind, right? If you're presented with two numbers, one's in meters per second, the other is in hertz, which, by the way, a hertz, right, is 1/seconds. So if I divide wave speed, meters per second, by 1/seconds, by 1/seconds, which is hertz, that's going to leave me with just meters. Okay? A couple things you really need to hold on to in this unit has to do with what is producing the variables here. What I mean by that is, like, say I vibrate this board, I can make a sound, right? And so that sound will come at you at a certain frequency, and that frequency is dependent on the source, right? Whatever is vibrating is or causing that wave. That's the source, and the frequency is determined. So you want to make a note of this. Is determined by the source. Okay. Now that frequency can be very fast, can be very slow, but whatever's causing the vibration or the wave is going to be determining the frequency. Okay. And now the amplitude, by the way, I didn't mention this before. So I've got this wave here, right? And this line represents the equilibrium position, the undisturbed medium. But then when the wave travels through it, just like the slinky you saw in last video, it moves the medium away from its equilibrium position. And the amount that it moves that medium away from equilibrium, we're going to call that the amplitude. That's going to be the maximum amount of displacement from equilibrium is our amplitude. So let me write that here. Amplitude is maximum displacement from equilibrium. Okay, and when you think of amplitude, think about the energy. So amplitude tells me something about energy, or it corresponds to the energy of the wave. Okay, so the bigger you displace that medium from equilibrium, the more energy there is. Okay, so amplitude and energy are directly related to each other. The other thing you need to know is, well, and that pretty much tells you what a wave is, right? Because we haven't really defined it yet. A wave is a disturbance through a medium that transmits energy. Or maybe a better way to say that it's a disturbance that transmits energy through a medium. Energy is what's being transmitted. Okay, awesome. Okay, so that medium, by the way, the medium is what's going to determine your wave speed. Okay, you're thinking about that. Though, if you think about the slinkies, right? When we stretched those slinkies, there was a lot of tension, and the waves were able to move really fast. But when they were loose, they were loosey goosey. The waves didn't go so fast. So the wave speed is determined by the medium. So when a wave can pass through multiple mediums, you might not know this, but you think about sound traveling through air, but sound travels through water too. And those water molecules are closer together, and so they're going to hit into each other a lot faster. And so when sound goes from air to water, it speeds up. And then it actually, when it goes through a different medium, like into a solid, it's going to speed up even more because those molecules are closer together and they can transmit it faster. And so that's another big point we need to know, that wave speed changes when waves change mediums. Okay. Now, frequency does not. It doesn't matter what the frequency of the wave is. When you go from one medium to the other, the frequency will stay the same because it depends on the source. It doesn't depend on the medium. So the last thing I'm going to do here is just, I'm just going to do like a couple example problems, okay? So let me move this a little closer. Let's say we have a medium where the wave speed is 120 meters per second, okay? Actually, you know what? Let's cancel that. Let's say it's 340 meters per second. That is the speed of sound in air. Okay, so we have a sound wave traveling at 340 meters per second. And let's say the frequency of that sound wave is 170 hertz. Okay? What is lambda? What is the wavelength? Okay, well, let's think about what we have been given. Is this on? Yes. I have to move this up a little bit, or move this down. I'll move it down to here. I know this is super high tech, guys. So the wave speed, that is V. That is frequency. If you're asked to find lambda, lambda is just V divided by F. So we would divide the 340 meters per second by the 170. I'm just going to call hertz 1/seconds so that I can see my units cancel out a little better. Seconds cancels out with seconds, and I'm left with 2 meters. Okay, so 2 meter stick long, that's the wavelength of this particular frequency of sound. A couple things you might encounter today is if they tell you there are me get rid of this real quick. If they say that 20 waves pass by, in 5 seconds, well, you're going to have to convert that into hertz, right? So your frequency is then 20 waves in 5 seconds. That's 4 hertz. Okay. All right, guys. That's probably all you'll need today. A couple of things to look out for when you're doing your calculations. Sorry. Is frequency will not change when you enter a new medium. It's only dependent on the source. Wave speed will. If you're given the amount of time that it takes a wave to go by, take the inverse of that, and that will give you your frequency in hertz. If you're trying to solve for frequency, you just have to rearrange this equation, right? Let's just look at the other two iterations here. We could say that if we multiply both sides by frequency, we could see that the wave speed is just lambda times f, lambda times frequency. Or if we wanted to solve for frequency, you can switch those two, and that is just speed divided by wavelength. Okay? So you'll have to make all those calculations today. But really, it's not too bad. It's one equation. I wrote it 3 different ways. And that's all there is to it. I hope you guys do well. I'm expecting very, very good results when you go through the Google form. And we will pick this up again tomorrow.